So good afternoon, everyone.
Welcome to this Wednesday lunchtime lecture. We're through number 11 in the series, and we're hard to believe that we've been running these for several months at this point, and I hope you've been enjoying them, whether you're a regular or someone who has just, I suppose, selected some of the more relevant sessions to your interests in the Climate Action Sustainability series. Just to kind of, as usual, give the brief overview of where we're coming from. Really, we're trying to share knowledge and perspectives around addressing national and global challenges, with next week being our final session of part 3 of the series next Wednesday, the 10th. We have had a huge range of perspectives, and we've had one previous session dedicated to transport, and we have today's session a very I suppose a different form of transport being considered in today's talk. As always, our speakers, and I believe Charles, thank you for doing this, has kind of positioned his work in terms of the national priorities, climate action, and indeed international focuses as well of the Sustainable Development Goals, for us to consider how we're framing our work around these perspectives. So today, it's a great privilege to introduce a colleague within the School of Engineering, Professor Charles Stuart, who joined Trinity in recent years. Charles might give a bit of a background to where he's coming from within this space. And having had a previous session maybe on road transport, I think we have to look at discussing other forms of transport. And it's great that Charles' focus today is about critical steps to decarbonising aviation for Ireland. This is a topic that features as part of his research, but also in terms of contributing to the work he's doing in terms of teaching around zero carbon transitions in mobility. Charles, thank you very much for joining me and for us. I'll stop sharing my screen, allow you to maybe introduce yourselves in a little bit more detail, and over to you. I look forward to the talk. In about half an hour or so, we'll have the Q&A for everyone joining. You're more than welcome to, as always, raise your hand later on if you want to ask directly. But the Q&A chat here is to track questions that can come in that I can field to Charles, and Charles can maybe see them himself. But also as well, we encourage you we're welcome to turn on your mic. We'll give you functions to allow that. So Charles, over to you. Look forward to the talk, and thank you very much for joining us this afternoon.
No, thank you very much, John. And of course, it's a pleasure and a privilege from my perspective to have this opportunity to speak a little bit on the topic of decarbonising aviation. In terms of my background, I joined Trinity in 2021 as a new assistant professor. A lot of that role really centres around development and delivery of a new course in zero carbon technology that I'll talk about later on. And I suppose this is clearly linked to that, and as part of the direct research that I'm doing as well within the Department of Mechanical, Manufacturing and Biomedical Engineering. So as John said, my intention is to talk for about 30 minutes. Knowing me, I may talk for a couple or 3 minutes more, but we'll try and keep it as tight as possible so we're not impinging on anybody's lunch or anything like that. A little bit of housekeeping first of all then, just to talk about alignment of the research to some of the larger frameworks that are being examined or focused on at the moment. In terms of Ireland's climate action plan, there are clear parallels to the transforming how we travel section. Decarbonisation of transport is one of the biggest challenges that we face, and as you'll see moving through these slides, aviation really typifies the challenges, or I suppose an exaggeration of what you see in all other aspects of transport. The aviation business is very important to Ireland. It's something you'll get a little bit of awareness of as well. And what we actually see is that aviation can potentially provide a very clear use case for hydrogen moving forward. And of course, the benefits of hydrogen to the wider economy in terms of energy security and decarbonising other sectors, are beyond dispute. It just needs that little bit of a leg up, so we're not in this perpetual chicken and egg situation where there's no hydrogen infrastructure because there's no demand for it. So hopefully this will become clear as we move through. In terms of the Sustainable Development Goals then, clearly there are links to affordable and clean energy. That's, I suppose, at the core of what we're doing. but also on the responsible consumption and production side. As you'll see in a moment, a significant proportion of effort is being looking towards closing the carbon cycle effectively. And aviation is not a straightforward decarbonisation case, as you'll see. So it's going to need fuel, but it's going to need a fuel which either produces no carbon at the point of use, or is something for which the carbon has previously been removed from the atmosphere, essentially. So that's just a little bit of, I suppose, brief overview there. Jumping straight into the content then, it's always worth being aware at the outset why this matters, why it's important. Aviation can sometimes get a little bit of a bad rap in terms of emissions, but it is worth being aware that the aviation sector connects the world in a way that no other means of transport can. It truly is unsurpassed in terms of efficiency, safety, and speed. The other little bit of context is, of course, in Ireland, we are an island nation. We are somewhat geographically divorced from the rest of Europe. And Europe doesn't just have emissions targets, it also has quite stringent mobility targets as well. One of those effectively says that you should be able to move door to door anywhere in Europe within 4 hours. So for us, that means aviation is quite important. There's not really many alternatives. And that's borne out in the fact that 90% of travel at the moment to Ireland is already by air. The other thing to be aware of is that the Irish economy is very heavily reliant on aviation. So there's about a €10 billion contribution to the Irish economy per annum from airports, and there's in and around 220,000 Irish jobs that hang upon a strong and sustainable aviation sector. So, clearly aviation is very important for Ireland. The flip side of that coin is that Ireland is also very important for aviation. We punch well above our weight in terms of influence in the global aviation business. 14 out of the 15 largest aircraft leasing companies are based in the Republic of Ireland. And in total, there's in and around €100 billion worth of assets which have been managed through Ireland. So that's aircraft and engines as well. The other bit of perspective is, of course, that Ireland is home to Europe's largest airline, which is Ryanair. And of course, from a little bit of a Trinity-centric viewpoint for a moment, the CEO of Ryanair, Michael O'Leary, is ex-Trinity. CEO of Qantas, Alan Joyce, ex-Trinity. And the ex-Director General of IATA, Willie Walsh, is ex-Trinity. So it's something that, without revolving in these circles, you may not be aware of, but it's, Ireland is a key player in the global aviation business. And what this all means that as we stare down the barrel of quite a significant transition in the sector, it's clearly very important that Ireland has a strong voice within the European sustainable aviation community. Aviation in some ways is more important for us than any of the other European states. And as we transition towards a low carbon future for aviation, it's very, very important that the technology agenda that is followed reflects Ireland's needs. And a lot of that comes down to policy side, even as you'll see later on as well. Now, the flip side of that coin is something that we're all acutely aware of, and the environmental impact of aviation is something that can't be ignored. So at the moment, the global aviation business or global aviation sector contributes about 2 to 3%, depends on who you listen to, towards global CO2 emissions. The challenge that we have is that even if nothing changed, that percentage value would increase over time because other sectors are able to decarbonize more easily and are doing so more rapidly. So this is a particular issue that the aviation sector has to try and grapple with. The reason why, or where the source of these carbon emissions is that it's a sector which is almost entirely reliant upon fossil fuels. I'm not going to turn this into a combustion lecture by any manner or means, but this is just a quick illustration of the reaction between octane, which is a reasonably good surrogate for Jet A1 or aircraft fuel, combusting alongside oxygen. You'll see that if you've got carbon in the fuel, you're going to have carbon dioxide in the exhaust gases. That's absolutely unavoidable. And the conversion ratio there is around 3.1 to 1. So we release 3.1 kilos of CO2 for every kilogram of jet fuel burned. And of course, we all know the moral obligation that we have to try to reduce carbon emissions. A day doesn't go past where you don't turn on the news and see some of the negative impacts that global warming are having. But beyond that, there are legal frameworks in place to make sure that compliance is adhered to. One of the big ones, of course, is the overall net zero greenhouse gas target within the EU by 2050. Aviation has a big role to play in that. We need to get CO2 emissions down by around 75% compared to the levels in the year 2000. That's facilitated via a couple of different emissions trading schemes or offsetting schemes, both administered by the EU and the International Civil Aviation Organization as well. So these put a price on carbon effectively. And then we also saw on the news a few years back how these regulations do have teeth. Ireland was facing quite a significant carbon tax shortfall, and that 150 million euro would put a significant dent in any year's budget for a country. So it's something that we don't only have the moral obligation for, we have a clear mandate from a financial perspective as well to follow these regulations. And what I've really been trying to communicate over the last couple of slides really is that a truly sustainable solution for aviation is one where the environmental aspects are complied with and adhered to, but also the economy is allowed to prosper, so that the business aspect or the business side of aviation and all the positive aspects that it brings in terms of connectivity has to be maintained as well. Now, in terms of the challenge then, as John mentioned, we've had a little bit of a perspective before on the road transport sector, but just as an overarching message, I suppose, for transportation, there's going to be no single solution to replace hydrocarbon fuels across the board. So I've illustrated here a graph which shows energy density per unit volume on the y-axis and energy density per unit mass, effectively, or specific energy on the x-axis. And you can see that our traditional hydrocarbon fuels are a very good compromise for both of these. They're energy dense. They're also very easy to store. They're liquids at room temperature and pressure. And all things considered, they are remarkably inexpensive. When you take the process of building an oil rig, floating it out into the ocean somewhere, drilling a few holes, you eventually hit oil, bringing the oil on board the rig, pumping it on shore, processing it, refining it, distributing it, putting it out to filling stations for the automotive case. That's all done for somewhere in the region of €1.60 a litre, and half of that's tax. So it's truly remarkable, actually, how inexpensive these are. Another little bit of context, of course, is that we rely on carbon-based fuels. So cell respiration, which keeps us all going, uses glucose, which is a hydrocarbon effectively with a little bit of oxygen tacked onto the end. So it's a sugar. And just when we're talking about aviation, it's worth being aware that fat is a remarkable energy storage medium, and it's very, very close to jet fuel. That's no coincidence, really. What you look at, if you look at some of the great migratory birds, such as the Arctic tern shown here, they can cover about 22,000 kilometers in 3 months. So what we ultimately see is that the aviation sector has converged on a fuel solution, which is very, very similar to what millions of years of evolution have resulted in. And that's just nothing other than an illustration of how difficult it's going to be to move away from hydrocarbons in that context. Making it even more difficult is that aviation is going to be the most difficult sector of the lot in terms of, even within transport, to decarbonize in a 2050 timeframe. It is worth being aware that these are already very, very efficient machines. So if you look at the CO2 emissions per passenger kilometer for a Ryanair flight in 2021 and compare that to a typical internal combustion engine powered relatively small car, it's approaching half the CO2 emissions per passenger kilometer at typical utilization levels. And that's in spite of the fact that there's an order of magnitude difference in terms of the speed of travel. Now, you could be forgiven for thinking, we're looking at a 737 Boeing here, doesn't look drastically different in some ways from the de Havilland Comet, which was around in the late 40s. But actually, even over the last 10 years, technological improvements have resulted in fuel burn reductions of about 2% per year, and that's significant. The challenge is that those improvements have really been completely outpaced by sectoral growth, and taking the COVID dip out of the equation, all projections, again, there's some variation, but all projections going forward show a significant growth in the sector. And that means that these small incremental improvements are not going to be enough. There needs to be disruptive change, effectively, in order to successfully decarbonize aviation. The final thing to be aware of in terms of the challenge is that, even though batteries are gaining quite a bit of traction in the automotive sector, they're really simply not an option for commercial aviation in terms of a primary source of propulsive power. At the theoretical limit for lithium-ion batteries, they're about 30 times less sort of specific energy, so energy per unit mass, than kerosene or Jet A1. And what that means is that if you took a Boeing 747-8 Intercontinental, it has a maximum takeoff weight of around 448 tons, I think. It can carry 470 passengers over 8,000 nautical miles. And that's all done with 178 tons of kerosene on board, held within wing-mounted tanks and a center body tank. If you wanted to replace that energy on board with what you would have for the capacity from lithium-ion batteries, the weight would balloon to over 5,300 tons, at which point, you clearly do not have an aircraft anymore. So the overarching message then is that aviation needs fuel. The question is, I suppose, which fuel can really deliver the reductions in carbon emissions that we need and at the scale that we need? There are a number of different fuel candidates. I'm just going to start with a brief overview of biofuels first of all. So you may not be aware, but biofuels are already something that are involved in our daily life. If you go to your local petrol station or filling station and you fill up your car with either petrol or diesel, it's not completely petrol or diesel. The petrol will be between 5 and 10% ethanol, and the diesel will be up to 7%, usually derived from rapeseed oil, blended in with the fossil fuel. So there's a couple of different pathways for producing these fuels. There's first generation fuels which come from these food crops like rapeseed. These achieve about a 20 to 50% reduction in net CO2 emissions. Now, of course, the way that happens is the crops use photosynthesis. Photosynthesis brings in carbon dioxide from the atmosphere, produces glucose, and that can then be processed afterwards. But because there are issues with land use change associated with these first generation fuels, we're not getting the benefit you might expect in terms of CO2 emission reduction. And that competition between food and fuel is something that is a real issue, and it's something that the EU, excuse me, have set out to try and limit very stringently, and you can understand why. So they've introduced a cap in state aid and a cap in terms of the overall permissible amount of transport energy use that these first generation biofuels can contribute to. The second option is to use effectively waste valorization of some shape or form. So rather than using direct crops, we use bio-waste or agricultural residues as the feedstock instead. Now, these can potentially achieve up to or sometimes greater than 100% reduction in overall net CO2, once the fuel is combusted, particularly for these algal-based fuels, which are sometimes called fourth generation. The big problem they have, though, is cost and scale. At the moment, they're produced in relatively small quantities and are quite expensive. Aviation, in particular, uses a lot of fuel. Even the road transport sector uses a lot of fuel, so scaling that up is an issue. The scaling is expected to come mainly on the basis of what's called tall oil or tall oil, which is from a pine wood pulping process. But what you actually see if you look at projections going forward is that the availability of these waste streams is actually not going to be any better in 2050 than it is today. And the reason for that is actually a positive. We're getting better and better at reducing and reusing and recycling, which means that there's less by way of waste in order to use. So that's a good thing, but it has the consequence that the scaling of these fuels is very much limited. Just in terms of the aviation sector, at the moment, sustainable aviation fuels, mostly from this biofuel pathway, represent less than 0.1% of total aviation fuel use within Europe. And the target is to get to 63% by 2050. So again, the scaling challenge here is quite remarkable. The other thing to be aware of is that these fuels are not a drop-in replacement. At the moment, they're certified only to be blended up to 50% with existing fossil fuel. So that's another issue. And the final thing to be aware of is that specificity is key in order to try to figure out how much CO2 we're actually avoiding by using these fuels. And what I mean by that is, depending on where the feedstock is sourced from, depending on how it is transported to the point where the fuel is refined, etc., that can all embed additional carbon, which has to be accounted for. And that's something that colleagues in the School of Physics are working very hard on at the moment, is to try to do that carbon accounting effectively. The gold standard fuel candidate really is hydrogen, from the perspective of CO2 emissions anyway. So it's a colorless, odorless gas at standard sea level conditions. The challenge with it is that at those standard conditions, it has such a low energy density that it's completely impractical to be used in a transportation context. You either need to pressurize it very highly, up to maybe 350 times the pressure inside a car tire, or cool it down to minus 253 degrees Celsius to produce a cryogenic liquid. And both of these obviously take energy, these processes. The great thing about hydrogen, though, is that it produces no CO2 at the point of use. So if you look at the reaction here, hydrogen plus oxygen gives water as an output. So that all seems great. You know, everything seems rosy in the garden when you look at it from that perspective. This is a relatively blinkered view, and it's one which you hear quite a lot about in the news, is this concept of tailpipe CO2. And that's effectively looking at the CO2 emissions from the point at which the fuel is supplied to the vehicle to the point at which it's used. So that's a tank to wake definition in the context of what I've shown here. Actually, the production and the distribution of the fuel, this well to tank aspect, can have a significant impact, as you'll see in the coming slide. So you may think that hydrogen is something that's way off, you know, it's quite aspirational, it's not produced in any quantities at the moment. Well, actually it is. There's already 70 million tons of the stuff produced every year around the world. And most of this is produced through, the vast majority, in fact, is produced through what's called a grey hydrogen pathway. So that uses steam methane reformation of natural gas. So even though the hydrogen produced this way produces no CO2 at the point at which it's combusted, the production process by using natural gas as a feedstock and a fuel produces a lot of carbon dioxide. It's actually about 830 million tons per year. It's difficult to visualize what that equates to, but it's equal to the combined emissions of Indonesia and the UK for a year. So highly, highly polluting from a CO2 perspective, even though the end result is not so. It's worth also noting that this hydrogen at the moment is used mostly for industrial processes like steel production and fertilizer production. So any of it that gets produced tends to get used on site. So there's no real distribution infrastructure there. What we clearly need is to scale the production of green hydrogen. It has the benefit of having no CO2 emissions on the entire well to wake basis. So that's the full, I'm not going to quite say the full life cycle because that has other connotations, but the full process from producing the fuel to the end point at which it's used. And this uses renewable electricity to split water effectively into its constituent parts. The issue is that it's very, very small in terms of its proportion of the hydrogen production in the world at the moment. It's only about 2%. The final fuel candidate then is electro-fuels or e-fuels. And just to reinforce the point again, I've already talked about how the big issue with biofuels is availability of the feedstock within Europe. You know, so there's just not enough of the stuff, and it's not just aviation that's looking for it. What we actually see is that road transport and other sectors are also putting up a lot of demand. So on their own, biofuels are not going to be the solution by any way, shape, or form. E-fuels then are a little bit different. So they take the bio-based feedstock out of the equation. They use fresh water, renewable electricity, and CO2 So it effectively takes green hydrogen and combines it with carbon dioxide to create a liquid hydrocarbon. The good thing about this is because you're building the fuel from the ground up, it can be a direct drop-in replacement for existing fuels like kerosene in the aviation sector. And actually, it's a little bit of a designer fuel to some extent, because you can, with that ground up philosophy, you can change the chemistry a bit and do some clever things to try to reduce toxic emissions, for example, which is an important aspect. And the key thing to bear in mind here is that this is a truly net zero carbon solution if we're using green hydrogen, which is produced using renewable electricity, and direct air capture for the carbon dioxide source. So any of the CO2 which gets emitted at the point of combustion is fed back into the production of more fuel, essentially. Now, that's just looking at the fuels by themselves. There are other implications to consider whenever you actually want to roll them out at scale within the aviation sector. One of the big things to be aware of is that, we can't wait until 2050 to make this happen. This has to, there's a bit of a phrase going around that 2030 is now. Well, 2050 is not very far away either. And ultimately, we need to create impact very, very quickly. This contrasts against the fact that aviation is a sort of high inertia industry. There's a lot of money involved, and safety is absolutely critical. There's no hard shoulder at 40,000 feet, so everything has to be right. So trying to develop a roadmap for how to roll these fuels out and scale them is of paramount importance. Because of the issues that I discussed a moment ago, what we're focusing on is liquefied hydrogen and this power to liquid sustainable aviation fuel. So we're just leaving biofuels out of the equation because say they're fundamentally limited. Looking at the hydrogen case, first of all, then you take your renewable electricity, you take some fresh water, pass the both of them through an electrolyzer, and that produces hydrogen gas. So I talked about how the hydrogen has to be liquefied to make it usable in terms of an energy density perspective. That energy that is needed for that process means that you need to put in about 1.73 megajoules of electricity for every megajoule of fuel that you get out. So that's a production efficiency of about 58%. The energy density then of liquefied hydrogen is only about a quarter of kerosene or Jet A. So that's a little bit of a limitation. But where we really encounter issues is with infrastructure. There just isn't any. Also for aircraft, there are no commercial hydrogen aircraft available. So you either need to take an evolutionary approach, which involves essentially stretching the fuselage to allow room for large cryogenic fuel tanks, as shown here, or a revolutionary approach, which uses something like a blended wing body design here to take full advantage of some of the aspects that hydrogen can contribute. But again, this is not a solution of tomorrow. This is a little bit more aspirational, a little bit further away. The other thing we can do then is take our liquefied hydrogen, combine it with carbon dioxide in a Fischer-Tropsch synthesis process, and produce a liquid hydrocarbon fuel. So because of that extra processing step, it takes a bit more energy. Production efficiency drops now to about 38%, but everything else remains exactly the same. So it's green lights all the way. Energy density is the same, distribution infrastructure and all is there, and we can use existing aircraft as well. So you could be forgiven for thinking, well, based on that previous slide there, it's a clear victory for the power to liquid sustainable aviation fuel. Where's the contest? Actually, grid capacity, renewable electricity becomes the limiting factor. Ireland's largest offshore wind farm at the moment is based at Arklow-Bank, and you would need to run that wind farm for 25 hours flat out at rated capacity to fill one Boeing 737. And Ryanair has the guts of 500 of these aircraft. So you can start to see where the scaling issue becomes a problem. And even though it's convenient, it takes 53% more renewable energy to produce power to liquid sustainable aviation fuel than it does to produce liquefied hydrogen. So again, at scale, that's quite a disparity and something to be aware of. The other limitation of hydrogen that I talked about is that it's about the quarter of the energy density of kerosene. But what we see in reality is that, Boeing designed a 737 aircraft to do 2,900 nautical miles as a design mission, but in reality, Ryanair only fly about a quarter of that on their average mission. So by definition, half of their missions are less than that. So all of a sudden, having a fuel which is 25% of the energy density of the existing fuel candidate may not be such a problem across the board. Of course, again, to contrast that, hydrogen does present some other challenges. If you've got a fuel that's less energy dense, it means you have reduced operational flexibility. So you can't, for example, fill the aircraft and do maybe 2 short haul runs before having to fill it again. You know, with hydrogen, it would have to be filled possibly every time. Turnaround time can be an issue because we're dealing with the leakiest gas that is known. So in terms of processes, procedures for filling, they're likely to be more time consuming. And even if we roll out hydrogen at scale, we don't envision that it will be available at every single airport in Europe. So that can affect the viability of different routes for such aircraft candidates. And ultimately, this means there's no simple answer. What our work tries to look at is to see how real-world operations can enable the uptake of low-carbon technologies going forward using comparisons such as these. And I just want to make the point that not only is there no simple answer, there genuinely is no single answer either. This can sometimes descend into a bit of an argument about hydrogen versus SAF, and that does not do justice to the depth of the problem or the depth of the challenge. In reality, we're going to need to basically use all the levers that we have available to us. You know, liquid hydrogen plus SAF plus technology improvements to reduce the amount of energy that's needed, plus carbon offsets, because this is not a single step change. You know, it is a difficult journey with a number of distinct waypoints, but figuring out what those waypoints are is part of the challenge, because as you'll see in a moment, everyone needs to invest and engage in this. The aviation sector can't do it alone. So this becomes a question then of utilization. If you've got all these different levers, at what point do you pull them, and how do you optimally utilize each and every individual one of them at the different waypoints as we move towards 2050? So it's a matter of trying to minimize the renewable energy demand, because as you saw from the previous slide, that is significant, and maximize the amount of CO2 that we can mitigate at each step towards 2050. So in terms of our solution then, the basis of it really is to try to do some detailed modeling to figure out exactly what is required to decarbonize aviation, first of all in an Irish context, and then extrapolating out a little bit further. So again, I'll touch on this a little bit more in the coming slide, but the fundamentals of this are a well-to-wake aircraft energy analysis to figure out what's needed in terms of the wider economy for infrastructure with power generation and hydrogen production. But one of the big aspects is engaging with stakeholders across the economy. That list of stakeholders is numerous and diverse. And as I mentioned in the previous slide, we essentially need to generate consensus and to get everyone to agree on a path forward and move in a way that, you know, we're not creating suboptimal supply chains. We're not having hydrogen aircraft before there's any hydrogen infrastructure to refuel them. You know, it's making it all go, I suppose, bit by bit as far as possible. So just in terms of what this all means then, as I mentioned, at the core of it, we're doing work on detailed physics-based aircraft modeling. That's for both current technology and future technology options, right the way out to a 2050 timeframe. And one of the big advantages we have is that we have real-world flight data through our partnership with Ryanair, and that means that the models can be validated and can be accurate. Because if you're a few percentage points out when modeling an individual aircraft candidate, by the time you scale that to an entire fleet, to an entire country, the errors are huge. We're also taking into consideration airline scheduling constraints, because, you know, this is a business, it's a high value business, and productivity matters in terms of the aircraft. So that features in as well. And then we're trying to basically, in terms of outputs, figure out an overall techno-economic roadmap for the sector. A fleet optimization platform, which again is a question of utilization as technology improves. How do we roll it out? On which routes do we prioritize to generate maximum mitigation of CO2 emissions? And then as well as characterizing what some of the wider benefits can be to society, we also aim to characterize the requirements, as I say, in terms of infrastructure, and also the general economic and environmental impacts for various different deployment strategies moving forward. So I just want to recognise at this point that this work is being supported by Science Foundation Ireland, and their support is very much gratefully received in terms of funding and training, also for the key project members. So it's part of the National Challenge Fund. It's a 65 million euro fund split across 8 different challenges, funded directly from the EU's Recovery and Resilience Facility. And you'll have realized already that this is not a wholly technical challenge. So this is not just an engineering centric thing, which is why we partnered with Trinity Business School to get to assist in some of the wider implications and looking at supply chains, and also with Ryanair to make sure that we can generate societal impact, and also to have real world data to base our modeling on and to validate it. Finally, then, just one other shameless plug before I finish. I'm a few minutes over time, but we're not too bad. If these areas are something which are of interest to you, then there is a program which I coordinate in Trinity, focusing on zero carbon technology. And this is very heavily weighted towards the fundamental engineering science, or the physics behind different power generation approaches and also different propulsion technologies. And it's not just aviation. We look at aviation, maritime, and automotive sectors as well. The research work that's done is aligned with the Trinity Research Centre for Low Carbon Technologies and also our Sustainable Aviation Research Centre. So project work and assignments are very much applied in their nature to real world problems. There are a variety of different study options. Top of that tree is an MSc degree, which is a full 12-month effort effectively, and you can then go for a postgraduate diploma, postgraduate certificate, or a micro-credential, which focuses on essentially a single module. One of the big benefits of the program is that we very heavily focus on flexibility. So it's something that we're aiming to ensure that both full-time and part-time engagement can be facilitated, even for employed professionals. So all of the lectures are delivered live in Trinity, they're live streamed online, and they are also recorded for viewing afterwards, which helps significantly if you're trying to balance work and further study as well. So I'm just showing the website there. If you have any interest or anything like that, you want to contact me by email, please feel free to do so. And yeah, that was all I had. Only about 5 minutes over time, so not too bad. And yeah, welcome any questions.
But thanks for your talk, and for those asking questions, really help delve into some aspects that you've discussed. Charles, obviously as well, you've shared details around your contact details and courses you're involved in. You can be found via Trinity quite easily if search Trinity and Charles Stuart. And yeah, if you can't, just contact us. We'll share details of what you've presented, including the courses as well as the presentation, with everyone that's registered, as always. Charles, thanks once again for your talk today. And I'm just going to finish out with a few slides as per usual. People know the drill for those irregulars. About in terms of his recent courses can be found via Trinity website through research and courses, or searching Charles directly. Indeed all our speakers throughout the series. Our last speaker, I think Charles is a nice segue into our last speaker, Professor Max Garcia Mefor from the School of Physics, who is actually working in the hydrogen space. So if any queries and questions that have arisen from today's talk over where hydrogen belongs and how it's going to be produced and what's needed to produce it, that segue will be the discussion today will definitely lead us towards our last speaker, Max, in the series. So thanks everyone for joining us. For those of you who are obviously registered, we'll share a recording and the details, and share contact details and program related information that Charles has discussed today. And as always, share up, even though we're in the last session of the series, we're now planning 2024. maybe only short, even though Charles talks about short, medium and long-term goals, we're only in the short term with this series, but hopefully hearing from you around what you like, what you find interesting in the series, and staying in touch will help us guide us in developing just as good a program as we did this year. So thanks again, everyone, for joining us. See you next time. Charles, once again, thanks for taking your Wednesday lunchtime, and for everyone taking your Wednesday lunchtime to be with us today.
Thank you very much, John. Thanks, everyone.
Take care. Bye-bye.